Now that we have an understanding of what vector fields are and how we can visualize them and how we can get vector fields as the gradients of scalar valued functions, our study of the calculus of vector fields is going to take two basic flavors. The first flavor is one we're going to start talking about today, which relates to something called the circulation of a vector field. This is, roughly speaking, a measurement of if we sort of walk along a closed path. So if we start at some place in the xy plane or xyz space or wherever our vector field is, if we start in one place and then we traverse a path that brings us back around to our original starting position, then the question that we're asking is, to what extent were we walking in the same direction as the vector field on our circuit? And to what extent were we walking in the opposite direction as the vector field along our circuit? One way to think of it is if that vector field was like a wind velocity field or something like that, and I walk along a loop, then was I mostly walking with the wind, or was I mostly walking against the wind, or was it a little bit of both? What was the net amount by which I was walking with or against the wind field while I was walking around my loop? So that's a measurement that we call circulation. And that's the first flavor we're going to talk about today. As we'll see in this chapter, each of these flavors of vector field calculus can be defined in two different but intimately related ways. The first is using an integral, and so that's where we begin today, with the idea of a line integral, sometimes called a path integral, sometimes called a loop integral if our path is a complete circuit where we end where we started. And so that's going to be a measurement of to what extent is the vector field pointing in the same direction as we are traveling along the parameterized curve. To what extent is the vector field have a component which is positive in the direction of the velocity vector of our parameterized curve as we go around a parameterized curve. So we'll spend most of our time, I think, today building intuition for that, thinking about what that line integral is supposed to mean, how we can predict whether a line integral is going to be positive, negative, or zero based on the orientation of the vector field and the parameterized oriented curve that we're using. And then we'll spend a little bit of time today doing direct computation. So actually computing out what is the value of this line integral? How much was the total extent to which the vector field aligned with the direction of the velocity vectors of the parameterized curve along the curve versus against the velocity vectors. Fortunately for us, we're going to see that in a lot of cases, directly computing the line integrals the way we're going to get exposed to today is not always necessary. And so we're going to, from this integral calculus viewpoint, also build in a differential calculus viewpoint over the couple of classes that come after this to say, here are some cases where instead of taking antiderivatives to try to compute this line integral, we can use derivatives instead and come up with a differential measurement of not circulation that's total along a path, but kind of infinitesimal circulation, the circulation near just a given point. And that measurement is going to be called the curl of a vector field. So curl and circulation are going to go hand in hand. Circulation is the integral idea. Curl is the derivative idea that goes along with this notion. The second notion is going to be a notion of flux, where instead of measuring to what extent does the vector field align with us, flux measures the opposite. To what extent is a vector field cut across us as we proceed along a path? And so that's going to let us define things like, to what extent is a vector field flowing into a given closed region versus out of a closed region in the plane or in 3 space. And that's going to give us a total measurement that we're going to call flux, net flux into or out of a region inside of space. And then an infinitesimal measurement from the derivative that's going to go along with that is called the divergence of the vector field. So those are the two main flavors of vector field calculus, the circulation and curl flavor, which is where we're going to start, and then the flux and divergence flavor, which is going to be the second version that we look at as we go through this chapter. So today is our first introduction to circulation in the form of line integrals. What are they? How do we interpret them? How can we make educated predictions on whether a line integral is positive, negative, or zero? To what extent does the path that we take from the beginning point to the ending point of a path in a line integral, to what extent does that matter? And what does that have to do with gradient vector fields? That's the big question of the day. And then how do we actually compute directly the values of line integrals from a parameterization of an oriented curve?